All right, let's get moving. Good morning. Let me take a quick poll. So, how many of you have completed Lab 4? Completed Lab 4. Wow, that's great. So, how many people have begun Lab 4? Okay, well that's good. I won't ask the last question. Okay, so well, I hope you're having fun with this lab. Lab 4 was designed to be almost like a mini project, and it sort of ties together a lot of the content of the entire course. And it's not unlike the kind of systems that people design in industry, in systems that go into a variety of devices, like, say, for example, digital CD players and stuff like that. A lot of mixed signal stuff goes in. Okay. So today, I'm going to continue with our discussion of energy and CMOS. CMOS will be a new topic that I will introduce. So in the last lecture, we spent a fair bit of time talking about energy and how to compute the energy of our inverter. So let me start from where I left off. And I've given you a couple of extra pages of notes today just to sort of tie it to the previous lecture. Right now, I'm going to start off on page 3. So what we saw last time was an inverter of this sort, Vs, Vn. And we said, let's study the situation where this inverter was driving a load capacitor C. Where did this load capacitor come from? Well, this inverter could be driving 1 or 2 or 3 or 4 other logic gates. Okay? So this C is the lumped value of the gate capacitances of all of those inverters. This may also include some component due to wiring capacitance and stuff like that. So, so for a inverter like this, we showed in the last lecture that the formula for the average power was so this was a static power independent of frequency, and this was called dynamic power, and it had some bearing. It's related to the frequency at which you clocked your circuit. So this was related to standby power, and this to dynamic. So what I also said is that I give you a bunch of numbers so you could compute the power, the power consumption of a chip that included 10 to the 8 gates, 100 million gates, and at a frequency of 1 gigahertz, and a bunch of other numbers. C was given to be 0.1 femtofarads. This is femto is 10 to the minus 15. So F was 10 to the 9. Vs of 5 volts. And so for these numbers, if you plonk them down in something like this, for 10 to the 8 gates on a chip, the average power would be 10 to the 8 times these two. So this would be 5 squared, which is 25, divided by twice. RL was given to be 10 kilo ohms. So twice 10 to the 4. And here we had CVS squared. So C was 10 to the minus 16, 0.1 femtofarads. Vs squared was 25, and F was 10 to the 9. So if you crunch through the numbers here, what you end up getting is something that looks like this. 10 to the 8 times this guy here. This is 1.25 milliwatts. Plus, this guy ends up being 2.5 microwatts. So, so this should come as a bit of a shocker. If I take 1.25 milliwatts and multiply that out by 10 to the 8, this says that each gate suffers a standby power loss of 1.25 milliwatts. So times 10 to the 8, I get 125 kilowatts. And this guy yields 250 watts. Okay, the 250 watts is manageable. It's still high. And just so you don't think that this is unreasonable, when the Pentium 4 first came out, it was consuming 170 watts of power. Okay, you should see the heat sinks on there. There's actually a huge heat sink with a fan built into the top of the heat sink. Okay, today it's down to more reasonable numbers like 100 watts and so on, but when it came out, it was in this range. So this is not, it's high but not unreasonable. But this, of course, is totally wacko. Okay, you may imagine carrying a laptop around and the sucker is, blowing 125 kilowatts. So that'll be fun. So clearly there's something wrong here. Okay, what this is saying is that this gate here consumes 125 kilowatts if there are 10 to the 8 of these on a single chip. Okay, so we clearly have to do something about this, otherwise our semiconductor industry, would fail. So anybody have any ideas? What do you think you might do here? What do you think you might do to this inverter to make this look better, to bring it down? What can I do? Anybody? Any ideas? What do you think? Well, the problem is that if I look at this 125 kilowatts, well, there's a VS term here, an RL term here. So I can increase RL. Okay, I can make RL 4 times, 8 times as large. That'll bring the power down somewhat. Anybody can think of any problem with increasing RL? If I make RL really, really large, will I run into other problems? Yes? Exactly, it'll slow down the inverter. Remember, the rise time of the inverter depends on how quickly I can charge this capacitor through RL. So if I make my RL really large, I will consume less standby power from hundreds of kilowatts to merely tens of kilowatts. But my gates will run as slow as molasses. Okay, so clearly that's not a trade-off I would like to make. But so I could reduce my voltage to maybe a volt, but that just reduces it by a factor of 25 Vs squared. So clearly this is not going to work. Okay, I have to somehow do something else, and that will be the topic of today's lecture. Also, I want to dwell for a moment on this term. So if you look at the spec sheet for the IBM's ASIC process that we handed out, if you recall, it talked about power dissipation of 0.006 microwatts per megahertz per gate. Okay, now you see where it is coming from. Per megahertz, that's because F is it's a multiple of F, the power. Second is that it's per gate, so this is the power per gate. So as I have more gates, I just have that much more power dissipation. It also says power supply voltage in the range of 0.7 to 1.3, right next to the power expression. So you can see why they tell you all of that, because both the voltage and the frequency and the number of gates come into the power equation. Okay, this really simple expression here, it's amazing how close this is to what people use for the dynamic power in chips. Okay. So as the next step, what I'd like to do is this guy. What do we do about that? Okay. So we've taught you to build gates in a particular manner, but it's a non-starter. So how to get rid of static power? How do I get rid of static power? Okay, to do so, let's build up a little bit of intuition. Okay, so so the intuition goes as follows. So let's say I take my inverter. Let me draw the circuit both in the on state and in the off state. So when Vin is high, I get the MOSFET turning on and has a resistance R on, and VO is the output voltage. Similarly, when Vin is low, so when Vin was high, VO was low because R on is much less than RL, so this voltage was low. While here, when Vin is low, the MOSFET is off. Okay, the MOSFET is off, and so I have an open circuit out here. And because of that open circuit, the voltage here was going to be high because Vs would simply appear there. So let's stare at this and see if we can build up some intuition as to what to do. So when Vin is low, I don't have any static power being dissipated because I don't have a connection from Vs to ground. Okay? The current I is 0. And Vs simply appears at the output. And the reason this is so is I have a switch here. So when this is low, the switch opens up and cuts the path from power to ground. So this is a nice situation. Here, when Vin was high, there is no switch that turns off. Rather, I get a connection from Vs to ground. Okay, so think about this situation here. The insight here is just imagine. Imagine if I could do the following. Imagine if I could somehow magically elevate RL to be a very, very, very large number. If I could make this so high as to make the power really low, only in the situation when the input was high. Okay? So imagine if I could do something like this. Imagine I could open circuit this guy, R on. So when Vin was high, if I could, instead of having an RL here, what if somehow I could make this RL become infinity? Okay? So in this case, output VO would be low. Okay, I get many benefits by doing this. One benefit is that, look, I've opened the switch here, so I don't have any standby current. Okay, the standby current is 0. Second benefit is that my output gets dragged down to ground. Okay, out here my output was Vs divided by R, Vs multiplied by R on divided by the sum of these two. Out here, I have a direct connection to ground and nothing to the power supply, Vs, and so therefore I have a nice solid low. So the question is that, can I get the situation? Okay, that is the key insight. So imagine that somehow, when this was high, I could get this to open up. Much like when this was low, I got this to open up. Okay, so think about it. So the intuition is that what I need is, instead of a resistor here, what if I had something like the MOSFET that I have here? So I had a MOSFET here that turned off when Vin was low. Okay, what if I did the complementary thing? What if I put in some kind of MOSFET here that would turn off when Vin was high? Okay, so much like the MOSFET turned off when Vin was low down here, imagine if I could find a device that would turn off when Vin was high. Okay, this would be on, but this would be off. So the behavior of this device would have to be complementary to this device. So So we need some sort of a switch. And to introduce this new little MOSFET device with the slightly different properties, let me quickly review for you the properties of the MOSFET that we know about. So our N-channel MOSFET, also called the NFET. This is what we've been seeing all this while. Is drawn like this. I have a gate, I have a drain, I have a source. And this guy is on when VGS greater than or equal to VT. Okay, and off when VGS less than VT. You saw this before. Okay, nothing new here. So what I need is a device that behaves in a complementary manner. Okay, so the device is a p-channel MOSFET. By the way, I must point out, till about 1983, 84, till the early 80s, that's exactly pretty much how chips were designed. Okay, using a NMOS, using a NFET for the switch looking down here, and a variety of different kinds of devices to be used as resistors. Okay, that's when technology began moving towards this new kind of technology I'm going to talk about, and that dramatically reduced the amount of power consumed. And the p-channel MOSFET was created, and this guy is called the p-FET. It's a complementary device that looks as follows. Okay, the difference here is that to show this is complementary, I'll put a little circle here. It has a gate. Okay, flip, just to make things a little clearer, flip the drain and source terminals. And this guy is on. And to distinguish the threshold voltage of this with the NFET device, let me put an N here to say that this is the VT for the N-channel device. VT for the N-channel device. And for this guy, this guy came on when VGS was greater than some voltage. So VTN could be, for example, 1 volt. So when VGS was more than 1, this turned on. In this case, I want this to turn on when VGS is some value which is lower than, or much lower than the source voltage. Okay, so this guy turned on when the gate voltage was higher. This guy should turn on when the gate voltage is significantly lower than the source voltage. Just the complementary behavior. Okay, so then VGS less than or equal to VTP. And in this case, the threshold voltage for the PMOS device, say, just as an example, maybe minus 1 volt. So this means that if the source is at, say, 5 volts, okay, then this device would turn on if the gate, for example, using that example, was less than 4 volts. So this is phi. If the gate fell below 4 volts, this guy would turn on. In this situation, remember, if this was at 0, the gate would have to be greater than 1 volt to turn on. In this situation, the gate has to be less than 4 volts if the source is at 5 to turn on. And it's off okay, so this is a complementary device that I postulate that behaves in a complementary manner. So the gate voltage rises, this guy turns on. And in this particular situation, when the gate voltage drops below the source voltage, this guy turns on. Okay, so one is the rising guy that turns on. In this particular situation, when it falls, the gate turns on and shows some resistance. In this case, the resistance would be R on. And to show that it's N-channel, let me say N. And in this case, the resistance when turned on would be R on P to represent P-channel. Okay, so now consider the following circuit for the inverter. So instead of my resistor, I put a complementary device. Okay, and that's it. So all I've done here is replace my resistor with a MOSFET that behaves complementary to the N-channel MOSFET. So this is my gate, my drain, this is my source, my gate, my source, and my drain. Okay? And this guy is called a pull-up, and this guy is called a pull-down. Okay, and the reason is that this guy pulls the output to ground when it's turned on, while this guy, when switched on, will pull this node up to Vs. So I pull it down or pull it up based on whether Vin is high or low. So let's look at the two situations. So let's say, as an example, my Vs is 5 volts, and let's say Vin in one situation being 5 volts, and another situation being equal to 0 volts. Let's draw the equivalent circuit in both these cases. So when Vin is high, I have my usual circuit. When Vin is high, this MOSFET as before, when Vin is 5 volts, the N-channel MOSFET below is turned on, and so I have an R-on resistance here. But remember, if Vin is 5 and Vs is 5 volts, then the voltage across the drain and the source, the source and the gate of this P-channel FET is now equal, 5 and 5. Okay? So this one will turn off. And that's the circuit that I get. The output is suitably low. In this situation, if Vin is 0, what happens in this situation? This is my output. If Vin is 0 volts, the lower device turns off. This is 0, this is 0, this guy turns off. And so that's the situation for the N-channel MOSFET. How about this guy here? What happens here? This is at 5. So let me just this is at 5 volts. Okay? And Vin is at 0 volts. Okay, so therefore, the GS of this is minus 5 volts. If this is 0 and this is 5, G, source and drain, GS is minus 5 volts. And minus 5 volts is significantly less than the threshold, minus 1 volt in our example. So this one will switch on. So, and if this one switches on, what I end up getting is, oops, R on P out there. So when this one kicks in, it pulls the output high and VO goes high. So all I've done is replace my resistor with a complementary device, which switches off when the input is high and switches on when the input is low. And the beauty of this is that at no point, assuming all devices are ideal here, at no point do I have a short circuit between the output, or do I have a current path from the output to ground, from the supply to ground. Okay, I have this turned off or this turned off. So this type of logic involving a PMOS transistor here and an N-channel transistor here is called CMOS logic for okay? It's called complementary MOS logic. That's what CMOS comes from. Okay, so I'm sure you've read in a number of places, oh yeah, it's most digital chips today use CMOS technology. It comes from complementary MOS. And complementary comes from the use of complementary transistors. N-channel, P-channel. Turns on when high, turns off when high. Turns off when low, turns on when low. Okay, they're exactly complementary to each other. So for the past, so what you've seen here has been the workhorse of the digital industry for the past 2 decades. 20 years, CMOS logic. Okay, and even the most advanced chip from Intel has an inverter that looks exactly like that. Okay, a lot, if you count all the inverters in the universe today, I would say a significant fraction of those look exactly like that. No difference. It's just so simple. So the key with something like that is there is no path from the power supply to ground, and so by that model, I do not consume any standby power. Okay, my standby power in that idealized model is 0. So let's compute P. So what is P dynamic? Let's use the method that we adopted in the last lecture and draw the equivalent circuit and compute the power. Okay, so I'm going to model the following situation. And assume that I drive a capacitive load C. Okay? And as an input, as I did the last time, I'm going to assume I have some input voltage, V in, that looks like this. The cycle time T, and the frequency is 1 by T. And let me assume that this is T1 and this is T2. Okay? And I'm assuming that T1 and T2 are both much larger than the respective time constants. Okay, the time constants for discharging here is C R on N. And here, the relevant resistance is R on P. The charging time constant is R on P times C. Okay, so T1 and T2 are assumed to be much greater than these two. So when you look at this, there is one other benefit besides the power benefit, okay, of using CMOS logic compared to NMOS. Okay, it not only cuts out my standby power, but there is another significant advantage, which is almost equal to the power advantage of this kind of CMOS technology. Anybody have any ideas? What's the advantage? What does your intuition tell you? Is CMOS going to be faster or slower than NMOS? Why? That's right. The key here is that the NMOS design I showed you earlier was relatively slow because it took me a while to charge up the load capacitor from the load from RL. In this situation, RL has now become really, really small. It's R on P. It's roughly the same magnitude as R on N. Okay, so if both of these on resistances are more or less equal and small, then the rise time will be of the same order of magnitude as the fall time, which makes this much faster than the NMOS. In NMOS, my time constant was RLC, and RL was pretty large. In this case, it's R on P C, and R on P can be made to be very small because when it's switched off, the resistance here is infinity. So in this situation, if I assume T1 and T2 are much larger than the respective time constants, I can go ahead and draw my equivalent circuit. So here's Vs. So for charging up, let's say this one is going to a 1 or to a high. So I have Vs going through a resistor R on P to capacitor. And this thing is a switch. So I have R on P, an ideal switch going to a capacitor C. This is my V out node. Okay, so it's Vs going through a resistance R on P and an ideal switch to a capacitor C. That's a charging circuit. For discharging, I have C discharging through an ideal switch with the R on N. So in this situation, I have an ideal switch R on N. Okay? So that's the equivalent circuit for something like this. So in this circuit, during T1, this guy is off, and this guy is on. On during T1, and off otherwise. This guy is on during T2 and off otherwise. Okay, so just imagine, this guy switches on, this guy switches off, this guy switches on, this guy switches off. Okay? And remember, this is exactly the circuit I had analyzed last time in the last lecture, and with the result given by the double asterisk. And that result was simply average power being C Vs squared F. That's the exact circuit we used to compute the dynamic power C Vs squared F. Okay, so we're done. And how did this come about? This came about because the intuition here is that I'm charging up the capacitor fully, and then I'm discharging the capacitor through this other side. Okay, and I'm consuming power, dissipating power in these two resistances during charge up and during the discharge. Half the power gets consumed during charge up and half during the discharge. So I'd like to go back to doing a few numbers here and taking a look at how, even with this expression, life can get pretty thorny as we go ahead into the next decade. Okay, so for our previous example, we'd assumed that 10 to the 8 gates, F was 1 gigahertz, C was 0.1 femtofarad, Vs was 5 volts, and I don't need RL anymore. Okay, why is it that I don't have any resistance component here? I don't have it here because the power consumed by the circuit is independent of those resistances, provided T1 and T2 are long enough, are much longer than the two time constants, R on P C and R on N C. Okay, so I don't have RL in my equation anymore. I don't have any standby power. So based on this calculation, the calculation I did up there showed that I had 2.5 microwatts per gate, and for 10 to the 8 gates, I had 250 watts for a chip with 10 to the 8 gates. So I'd like to dwell on this. If you can move over to page 8 in your notes here. Let me dwell on this for some time and pontificate on a few things. First of all, this number, as I said before, is high, but not a disaster. Okay, so it can use this in laptops. Okay, but it's quite okay for a desktop or a server and so on. Okay, if you just go and put your ear to a pedestal computer, you'll always hear it making a sound. Okay, and that sound is because of a big fan that's inside it. And if you have a big enough fan, 250 watts is not such a big deal. Okay, but this is certainly a real problem for mobile devices. Okay, for a laptop, this is unthinkable. Okay, so we have to deal with this. The second issue is the following: that it's 250 watts for 1 gigahertz. Okay, now in the fastest Pentium 4s that money can buy today are what? How many gigahertz? What's the fastest Pentium 4 you can buy today? What's that? So does anybody have a 4 gigahertz Pentium 4 here? Ah, darn, you beat me. Anybody have a 3? 3 gigahertz? Oh, cool. Couple. So I have a couple 3 gigahertz machines, and our lab has a whole ton of them. so if Intel comes out with 4 gigahertz machines today, they've been going up by about a gigahertz roughly every year for the past couple of years. And within 3 or 4 years, we're going to see chips, microprocessors that are in the 5 to 10 gigahertz range. Okay, assuming that all other things stay equal, which of course they're not, but just to give you some insight here, if I clock these guys and build circuits that are 10 times faster, then I very soon go up to 2.5 kilowatts. And I said, again, all things being equal, which they're not. But just to give you a sense, as I increase my frequency, so does the power consumed by the chip. Okay, so I really have to do something here. So if I stare at this equation, C Vs squared F, I want to increase F because people will buy computers if I have higher frequencies. Okay, and Intel has managed to use its marketing campaigns to pretty much convince consumers that high frequencies are a good thing. Okay, and whether they really mean anything or not, that's a different issue. So we got this huge power for assuming 5 volts. Okay, so it turns out that microprocessors, as they come out, newer and newer versions run at lower and lower voltages. Okay, they invent technologies that use lower and lower voltages and go from VS 5 volts to today VS on the order of 1.5 to 1 volt, somewhere in that range. So the moment you do that, you get a 25x reduction in power. Okay, so in going from 2.5 kilowatts, you would now come down to something on the order of 100 watts, which is again much more reasonable. Again, all else being equal, it turns out that the capacitance of devices also changes as you go to smaller and smaller devices. Now, 100 watts is also pretty high, and still not good enough for mobile computers. So there are many, many other tricks that people use to get even lower powers. One trick is to play games with the clock. Okay, what you do is, let's say, for example, in some computation, you are not going to be using your floating point unit. Or let's say you're not going to be using your integer adder unit. Okay, so what you can do is you can turn off the clock to those devices so that those devices do not even switch when they're not working. Okay, if you turn off the clock to a device, the device isn't going to switch, and so it's just going to sit there in limbo without consuming any power. It's equivalent to turning off both transistors. If you turn off both the PMOS and NMOS somehow, okay, it's not consuming any power. And by doing that, you can further cut down the power. So if you can idle some of your function units, it's called idling a function unit. Idle a function unit for, let's say, half the time, okay, you would cut down power by another factor of 2. We can idle them 75% of the time, come down to 25 watts. So those are the classes of tricks that people play. I'm going to stop here and allow the underground guide folks to do the survey. But suffice it to say that the power discussion I've gone through with you is a very high-level discussion as to the real thing. In real life, what actually happens is that there is a fair amount of standby power even for CMOS logic. It turns out that although I don't have a path from VS to ground for my 2 transistors, it turns out that there are many leakage currents. Okay, currents leak through all kinds of places, through the drain of your inverter and so on and so forth. And so there is some standby power. So let me show you a quick demo while I guess the review handouts are going around. And this just shows the temperature of my CMOS inverter. And as I increase the frequency, you can just watch the temperature go up, and hopefully we'll blow this transistor. So I'm increasing the frequency, as you can see on the side here. And higher frequency implies more power consumption, more temperature. Okay, and hopefully we'll see some smoke coming out of...
He's gone.
Okay, I think I blew the inverter. So the output is gone. So it's at 110 degrees there, and I just blew it. Sometimes we've seen smoke come out, but I guess today is not one of our lucky days. Okay, so let me stop here and have the underground guide folks go through the reviews.